Hi, welcome back to General Chemistry. My name is Chuck Wight, and today we're going to talk about elements and moles. No, not that kind of moles, the chemist moles. We'll talk about the periodic table and the structure of the periodic table and why it's structured the way it is. And we'll talk about Avogadro's number, which defines the size of the mole. Now, the periodic table was originally organized by Dmitry Mendeleev in the mid 1800s. He was a Russian chemist and a very clever guy. The rows in the periodic table are arranged by mass, so increasing atomic number, which is determined by the number of protons in each elemental atom. And the columns are organized by the chemical properties. And so you can see that in the first row there are only two elements, hydrogen on the left and helium on the right. In the second row of the periodic table there are 8 elements, and the third row has 8 as well. The fourth row has 18 because there are 10 extra metal elements inserted in the middle, and so on. So we have different series of elements which are organized in this way. Now, the first column of the periodic table is composed of alkali metals, lithium, sodium, potassium, rubidium, and so on. And all of the alkali metals have very similar chemical properties. They form metals which are ionic and have one valence electron and form one strong ionic bond to other elements. The second column contains the alkaline earth elements, beryllium, magnesium, calcium, strontium, and so forth. And all of the alkaline earth elements also have similar properties to each other. They form two strong ionic bonds to other elements. Then there's a large number of metals called the transition metals in blue. There are 10 columns there. Then finally we get to columns of elements which are not metals. The purple columns are metalloids, which are often used in semiconductors. The green elements are the traditional nonmetals. The yellow column, which is the next to last column in the periodic table, is composed of halogens. They also are very reactive, form one strong bond to many other elements. And then the final column is the inert gases. Helium, neon, argon, krypton, xenon, and radon are all contain atoms which have complete shells of electrons and don't like to form chemical bonds to anything. And so the columns of the periodic table are determined by the chemical properties, and the rows are organized by increasing mass. Now, Avogadro's number is just a number. It's a convenient number for chemists because it defines the mole. And the easiest way to think about Avogadro's number is like many other numbers that we have, like a pair. A pair always refers to two things. So a pair of shoes is two things. A string quartet is 4 musicians. A trio is 3. Duet is 2. Quintet is 5, and so forth. A dozen eggs is always 12. Except for a baker's dozen of rolls or something is typically 13. A mole of molecules is 6.022 times 10 to the 23rd molecules. And so that's a very large number. Why in the world did we choose that? Well, it turns out that a mole of hydrogen atoms is the number of hydrogen atoms that it would take to form 1.00792 grams of hydrogen. Wow, that's a lot of hydrogen atoms. In fact, it's 6.022 times 10 to the 23rd hydrogen atoms. So a mole of water occupies 18.01 milliliters, or 18.01 grams, and that would be 0.61 fluid ounces of water. So that says that a mole of something is just a macroscopic amount of something, usually small enough to hold in your hand. But it represents the same amount of stuff in grams as the atomic mass unit is for a single atom. So why is this useful? Well, let's suppose we wanted to know what mass of hydrogen gas, H2, will combine with 5.5 grams of oxygen gas, O2, to form water. Well, let's see. A rough guess would be something less than a gram. And we know that because if you have 5.5 grams of oxygen, you need twice as much hydrogen as oxygen, but hydrogen weighs much less than oxygen. So it'd probably be something less than a gram. So let's try to figure this out. First of all, we need to know the balanced chemical reaction for forming water from hydrogen and oxygen. And that's depicted in this equation. So we need twice as much hydrogen as oxygen to form 2 molecules of water. And next we need to know the molar mass of oxygen. Well, each oxygen molecule consists of 2 oxygen atoms, and if we look in the periodic table of elements, we can find out that the atomic mass of oxygen atom is 15.994 grams per mole. And so twice that is 31.998 grams per mole, and so that's the molar mass of O2. 1 mole of oxygen molecules weighs 31.998 grams. So we can now calculate the number of moles of oxygen in 5.5 grams by taking the mass of oxygen, 5.5 grams, and dividing by the molar mass, 31.998 grams per mole. And what we get is that the grams in the numerator cancels the grams in the denominator. And because moles is in the denominator of the denominator, it flips up to the numerator. And we find that we have 0.01719 moles of oxygen gas in 5.5 grams. So the first step in determining what mass of hydrogen gas would be determining the number of moles of hydrogen gas we need. Well, we know from the chemical equation that we need twice as many moles of hydrogen gas as oxygen gas. So 2 times 0.1719 is 0.3439 moles of hydrogen gas. That's how much we need to combine with 5.5 grams. Now that we know the number of moles of hydrogen, we have to back calculate the mass of hydrogen in grams. And again, so we're going to need to know the molar mass of hydrogen. Well, if we look in the periodic table, we can find that the molar mass of hydrogen atoms is 1.00794 grams per mole. And so for hydrogen molecules, which have 2 hydrogen atoms per molecule, it's twice that much, or 2.016 grams per mole of hydrogen gas. And so to calculate the mass of hydrogen that's going to combine with 5.5 grams of oxygen gas, we take the number of moles of hydrogen gas, which we calculated as being 0.3439 moles, and we multiply by 2.016 grams per mole for hydrogen gas, and that tells us that we need 0.6933 grams of hydrogen gas to combine with 5.5 grams of oxygen gas to form water. And this 0.6933 grams is somewhat less than 1 gram, so it agrees with our initial guess that the amount of water that would the mass of hydrogen that would combine with 5.5 grams of oxygen to form water, it should be somewhat less than 1 gram, and it turns out to be 0.6933 grams. So the reason it's useful to know things like molar masses and moles of hydrogen is that you have this simple relationship. 2 to 1 is an atom to atom or mole to mole ratio of hydrogen with oxygen to form water. But in order to convert that to mass, we need to use the molar masses of oxygen and hydrogen to figure out the actual mass of hydrogen that would combine with 5.5 grams of oxygen. Next time, we're going to talk about molecules and chemical equations. We'll talk about ionic and covalent chemical bonds, the naming conventions for molecules and compounds. We'll talk about determining the chemical formulas from experimental data and balancing chemical equations. See you then.